is hard one. It's carefully control the number of parameters in this neural network. This is the hard one. Okay, next I will introduce our second result and high manifold hypothesis. This result we use a constructive method to get the following result. States that the M be a d-dimensional compact Riemann manifold and the target function is S times continuously differentiable function. We can find a deep residue network phi with a fixed width depending polynomially on the input dimension or ambient dimension capital D and the depth L. This neural network can approximate the target function with a uniform approximation error bounded by this type of estimate. Okay, you can see here the network complexity grows like the number of the weights equals the order of the epsilon to little d of the 2s. Here is the little d. In our second part is the capital D. But now we're using the manifold hypothesis. This is become the little d. Here, our result, the C doesn't depend on the capital D. We improve the following existing results. The constant C in the following results, the C still depends on the capital D. Our result, our constant not depends on capital D. We improves the following result. Okay, let's quickly review the main idea of our constructive approximation result. The first, we build an atlas UI phi I from 1 to Cm, where the phi I is a affine map, and the C sub m is the number of the chapters. We construct the partition of the unity, the at I of x, such that the target function f naught of x can be written as this summation. Just using the partition of the unity. Okay, in this picture, you can see this is the f naught from the manifold to this real number. We can also express this f naught as the f naught composed with the phi I inverse, composed with this phi R. So this path from manifold to real number, all these paths are equal. So we also can express the target function f naught as this summation. Okay, in this summation, the main step is to construct a neural network to approximate this affine map. But you know, this affine map is easy to construct a neural network to realize it. It's very easy because in the neural network, one step is affine linear transformation. So easy to approach. But why this is difficult to construct? Just keep in mind that the domain of this phi I is UI instead of the entire manifold. But if you construct a neural network, the constructed neural network don't know the domain of this phi I is UI. It will works on the entire manifold. So just like this. We can only construct a neural network to approximate the f naught composed with phi I inverse composed with phi I tilde of x instead of the phi I of x. This phi I tilde is the extension of the phi I on the entire manifold. So we noticed that the many papers didn't consider this step. So I don't think their result is correct. So there will cause a problem. Just like this f naught of x is not equal to this summation. because the domain of the phi I is ui, but here the domain of the phi I tilde is not ui. It's on the entire manifold. So how to solve this problem? This is the key step. We use the above the lemma by the Shang, Koenig, and Kolyfman, and use the property partition of the unity at I. We construct the following. This new function fi hat of x equals the at I is the partition of the unity function times the ReLU function of the f naught composed with the phi I inverse composed with the phi I tilde inverse phi I tilde of x plus t of x. What is the t? What is this t? The map t is obtained by the above the lemma and can be realized by a neural network. So this new function fi hat has the following properties. For example, the f naught of x equal to summation of fi hat of x. So we solve this problem. We construct a new function. We can express this target function f naught. Okay, now our next task is to construct a neural network to approximate this fi hat of x. There are the 4 parts. You can say each part can be approximated by a neural network. Especially in this step, you can say this f naught is defined the manifold contained in the high dimensional space, right? But the f naught composed with phi I inverse. This function is defined in little d, defined in low dimensional space. Now we use the previous theorem to construct a neural network to approximate this GI, because the GI is still as times continuously differentiable function. Okay, next I will introduce an interesting application for our new approximation result. To this result, to improve the generalization error, let's consider a non-parametric regression problem corresponding to n observations. Xi, yi, I from 1 to n. The xi is in this 0, 1 to capital D, this unit cube, and yi is a real number. The yi equals the f naught of the xi plus the noise epsilon I, or the error epsilon I. This is the target function f naught is still alpha Hodak continuous function. The following technical assumptions is about the xi and the errors epsilon I. Okay, now what is the generalization error? The generalization error. In our hypothesis space, that is the neural network class, we can construct the empirical risk. We can compute the empirical risk minimizer f bar. F naught is our target function. The distance between these two functions is generalization error. There is a little difference from the previous picture. So now the optimal generalization error using the deep ReLU neural networks is the order of the n to minus 2 alpha of the 2 alpha plus capital D. Here the n is the number of the samples. But we can say this exponential term still depends on capital D. This means the generalization error still suffers from the curse of dimensionality. So let's revisit the problem under the manifold hypothesis. we assume the data lies on the d-dimensional manifold M contained in the R capital D, where the little d may be much smaller than capital D. We construct the following hypothesis space, that is neural network class. That is the network class. This class consisting of the neural network like this. The G is a neural network composed with a affine map. Composed of affine map. The affine map is defined as follows. This formula. This A is the random matrix from the R capital D to R to D sub E. So now our task is to approximate this target function f naught, just to compute the empirical risk minimized is phi bar. This phi bar to approximate this target function f naught with this arrow bounded by this type of estimate. Okay, now we need to care about the two things. First thing is exponential term. Exponential term is D sub E. Before here is the capital D. This we know this DE is the effective dimension. Just depends on the manifold dimension, little d. The second is this C, the constant C.
Recording in progress.
The constant C is the independent of the capital D. Our result improves the prior results by the Shang, Habo, Nakada, Imazumi, Chen. Okay, let's move on to final part. I will give some remarks. In our research, we derived an optimal approximation rate of deep level neural networks for alpha smooth Kodak continuous function with the smoothness alpha between 0 and 1. And for S times continuously differentiable functions with defined on unit cube 0, 1, capital D. And the manifold hypothesis, we apply the both non-constructive and constructive approach to achieve approximation estimates that are completely independent of the input dimension capital D. Using our new approximation estimates, we improved the generalization error under the manifold hypothesis. This hypothesis obtain an estimate which is also independent of the input dimension capital D. But the approximation results we presented above are derived using the deep ReLU neural network, where the activation function is a ReLU function. If we choose the different activation function, the approximation properties may be very different. If you are interested in this topic, you can refer to Yaroski 2021's paper. The following are our papers. The first is published in the neural networks. For the second paper, we are ready to submit. That's all for my presentation. Thank you.
Thank you. All right, thank you, G. So let me start with any comments, questions from the audience. Anybody online that would like to ask questions at this moment?
Yeah, sure. Is this a discussion with the audience or without the audience?
This is still with the audience. This is the public discussion.
Okay, so maybe I'll reserve my question for when we are face to face with the candidate.
All right, yes. Okay, yeah, definitely, we will have more questions later, right? And this is usually the moment where we ask, you know, the public if anybody has any comment. All right, so with that, I will also save my questions for later, right? So, so with that, we thank you for attending, and as I told you, right, we continue in our committee for the you know, committee discussion of the thesis. So you are invited to step out, and so this may